your brains back into algebra because that's where you're going next year. So I'm going to get rid of my face. You don't need to see my face. So here's the deal. Now, Sam, pay attention, please. So when we're looking at vertex form, this is a really nice form when you're graphing because this h right here, this is the x value of your vertex. Okay? So when it's, did you guys do vertex form last year? Okay. So this is the x value of your vertex. Okay, and remember, the vertex of a parabola is either the maximum or minimum point. It's the bottom or the top of your kind of your curve. And then k, that is your y value of your vertex. That's the y value. Okay. Now, here's the deal. So what we want to be able to do, if we didn't have access to Desmos and we wanted to graph this equation, we probably would want to put it in vertex form. Now, vertex form requires you to write part of the problem as a perfect square. Did you guys see that? So, with that being said, sorry guys. With that being said, what we want to do in vertex form is we want to go ahead and we want to complete the square right here. So here's an example where you have to complete the square. Whenever you're converting from standard form to vertex form, you're most likely going to have to complete the square. So here's an example of completing the square when it's absolutely necessary. So what we're going to do is this is kind of in standard form right here. We're going to write it in vertex form. You guys with me on that? Okay, so here's what we're going to do. The first thing we're going to do, let me kind of just first thing we're going to do now, if there was a remember when we complete the square, we like to have a 1 coefficient here, and I chose a pretty easy problem where we didn't have to divide everything. So first thing, I'm going to rewrite this so I have x squared plus 4x, and then I'm going to put a plus blank plus 6 plus another blank. You guys see that? Now, what this blank is going to be, ladies and gentlemen, is it's going to be my new C. Now, oh, by the way, I'm not going to say plus, I'm going to say minus. Okay, why would I do 1 plus and 1 minus new C? It cancels out. So basically, ladies and gentlemen, what you're really doing is you're adding 0 to this entire equation. Does that affect the value of the equation if you add 0 to it? No. So if we add a new C and we subtract a new C, basically we're just adding 0. Now, why do we want to do this? Well, here's the deal. What is our new C? Our new C is b over 2 squared. You guys see that? So what number are we going to put in for b, class? 4. So we put 4 over 2, and then we square that number. Well, 4 over 2 is 2. Square is 4. You guys with me on that? So we're going to put a 4 here, but then we're going to subtract 4. So again, did we change the value of this equation right here? No. We're just adding a 0 to it. So why would we do that? Well, let me come down and kind of rewrite this a little bit. The reason why is when you follow those steps that we just kind of did, we completed the square. So what we can do now is we can write this first part right here as something squared plus or minus something out here. You guys understand that? No. So, okay, so so we can do this math right here. What's 6 minus 4? 2. You guys see that? Now, remember, and this is just y equals out here. Okay, well, how did we complete the square? Well, let me rewrite this here. So we take the square root of this and put it here, right? You guys see that? What's the square root of x squared? X, okay. Now, we take the square root of this, and now, oh, by the way, this is a plus sign right here, right? So we put a plus right here, okay? And what's the square root of 4? 2. So what we now have it in is we have it in vertex form. Now, why is that helpful? Okay, so stop for us. Okay, stop for a second and just think about what we did yesterday with completing the square. Remember, our Our new c is negative b over 2, just b over 2 squared, right? Now, why do we like that? Well, we like that because we don't have to solve for anything like we did yesterday because we're not solving for x, we're graphing it, right? You guys see that? Okay, now, think about this. Vertex form is y equals x minus h squared plus k. So if I want to know what the vertex of this parabola is, now I can just simply read it off of the equation here. Do you guys see that? So what is the x value of the vertex, class?
2.
It's not 2. Remember, if this is minus, but this happens to be a plus,
Dude, I don't know. I tried.
so that's going to be negative 2. It's opposite. Remember, this is always going to be a minus. If it happens to be a positive number, then it's actually negative. It's always opposite. This is always minus. So if this is a positive, then you know it's a negative number right here because it's opposite. Look at the vertex form. It's always x minus h.
Right.
Here we have x plus h, right?
Right.
So we have to do opposite. If it's a plus, it means we had basically what we have here. If it's truly a plus sign, if we wanted to rewrite it a little more out, this is really minus negative 2. Isn't minus negative 2 just plus 2?
Right.
So that's why we would say it's negative 2. You guys see that? That's simplified out to plus 2. What is the y value of the vertex, class? 2. Now, we can go back to a in this case is 1. It's the number in front of, by the way, it's a. A is 1, and it's a positive 1. So what do we know? And nothing else, I know that I have a parabola. If I want to graph this parabola, let me just put a new page up here. Sorry. I want to do a new page. No, I don't want to do a new page. I just want to make myself some room. Okay, if I wanted to do a parabola, it's going to give myself some room. Okay, and I wanted to graph it. Okay, I know that it's going to face up because a is positive. Okay, and and a is the same a that it's going to be in here. Notice this is a positive 1. So my parabola is going to have a minimum value. You guys understand that? It's going to be facing up. Again, this is stuff you should have learned last year. So, and then your vertex is going to be at negative 2, positive 2. So your vertex is going to be right here. You guys see that? Now, your vertex is at negative 2, positive 2. So now your parabola has to look like this.
Legally, yeah.
See that? It has to look like that. Now, here's the deal. If I put this thing into the quadratic formula, if I used actually the standard form and put this into the quadratic formula, this equation, what do you think is going to happen in the quadratic formula? You're going to get a negative under your square root. Why do I know you're going to get a negative under your square root? What is the quadratic formula finding, ladies and gentlemen? What does that answer represent? Think about it. Use your brain. Turn your brain on. That answer represents where this parabola is going to cross the x-axis. In the quadratic formula, when you get 2 answers, or you get 1 answer, whatever, that's telling you where it crosses the x-axis. Does this thing cross the x-axis? No, it does not have any real solutions. It does not cross. That is going to be represented in the quadratic formula as a negative under the square root. There's no real negative numbers under the square root. You guys understand that? So there's a connection. So this all is completely logical. Vertex form helps us graph it. I was able to graph this. Did you put this in your calculator? Does it look kind of like this? Yeah. And I don't know anything about this, but I know it faces up, and I know the vertex is right here, so I can draw a quick sketch of it. Vertex form, standard form. We have to complete the square to get one to the other. You guys see that? Okay. So that's a good example where we would have to complete the square. Okay, so I need those algebra sheets. Okay, let's do this. Let's make them due by the end of the day today. Sound good?
Can we turn them in?
You can turn them in now, make sure your name's on it, or you need them by the end of the day today. During 7th period, I'm going to do a ton of grading. Anything that's there, I know Tegan's stuff is over there, Martin's stuff is over there. Okay, whatever.
you want us
Because it's
to-
not negative.
Yep.
So just that you
Yep.
don't need to graph it.
Nope. Okay. The parabola, I had a question. Why is the parabola not facing down?
So you just want
Yep. Because the parabola the A is positive. Okay. Now, Austin, your question was why is it not facing down? If this was a negative right here, then it would face down. Austin, does that make sense?
Oh, yeah. Well, I see.
Okay. And then, guys, if that was a negative, then we would have a solution because it would point the other way. Okay. If that was a negative A coefficient, then we would get our two solutions because it would look like this, and then we would get those two solutions right there. You guys see that? Okay, get ready to take a ton of notes. Okay, I'm just letting you know we have some more. We have our what I call my chord theorems. Okay, so just write the first one down, and then we're going to use this circle to explain it. Okay, so everyone, if you want to draw the circle, fine. If not, you can just write the words down. You're going to be doing a lot of writing today, and you're going to need these theorems on your test. Okay, so basically, we have some extra chord theorems that I want to go over, okay, with you guys. So you will not have any delta math on this, I don't believe. So you're going to be responsible for this, so you got to pay attention. We'll do some examples here. Okay, so a couple things we want to talk about. We're talking about chords and radiuses and diameters. Okay, so we're going to be looking at chords today, and we're going to look at the relationship between chords, radiuses, and diameters. Okay, so the first one, and these are pretty obvious things. So the first one says congruent central angles have congruent chords. So if I look at this center point right here, and I construct a central angle from this center point, okay? So I'll come over here, and I draw a central angle here. So I draw a central angle here, okay? And I draw a central angle here. Okay. And then I draw a central angle over here to the blue one, and I draw another radius here to create these two. Okay, so we get this hourglass looking thing. Okay, first of all, this angle, so let's give this some letters here. So this is A. If you want to sketch this out, that's fine. B, C, D, and E. Okay, so first of all, I know that angle ACB is congruent to angle DCE. Why do I know those two angles are congruent, guys? They're vertical angles, right? Okay, so these two central angles are congruent. So I could put little congruent symbols here, right? That's telling me what this theorem says is that means that AB, chord AB is congruent to chord DE. Okay, you guys see that? Pretty simple. It's saying if these two central angles are congruent to each other, then these two chords are congruent to each other. Go ahead. Now, this is an if and only if statement. Okay, statement 2 says congruent chords have congruent central angles. So if I know that AB is congruent to DE, which I do here, then even if these were not vertical angles, I could say they're congruent because their chords are congruent. You guys understand that? Questions there? Okay. Pretty obvious stuff, right, guys? Questions? Okay, this is going to go away in a second, so I'm going to give you guys a chance to copy down.
I can't see the fourth one.
I'm not to the fourth one yet. I'm on number 2.
Yeah.
All right. Now, what I'm going to do now is I'm just going to undo a bunch of stuff. Is that okay? I want to go back to the original part of this problem here. So I'm going to go back, get rid of these. Okay. I want to get rid of this, 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 and this. And I want to start back there. And what letters were these again? What letters? What was here? What? An E, right? Okay. Now, the next one says chords equidistant from the center point are congruent. Now, when we're talking about a point to a segment or a line, and we're talking about distance, remember, there could be multiple distance between C and the red line, right? This could be a distance. 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 So when we're talking about distance between a point and a line, what kind of distance are we talking about? Perpendicular distance. So we're talking about a perpendicular distance. So what is this theorem saying, guys? If chords equidistant from the center point are congruent. So if I know that these two chords are equal in distance, so they have to be right angles. You guys understand that? We've talked about that, haven't we, in here? And we know that this segment here is congruent to this segment here. Okay, you guys see that? Then we can now say the red segment is congruent to the blue segment. Why? Because they're equidistant from the center point. How do we know they're equidistant from the center point? Because first of all, their distances are perpendicular, and that's the definition of distance, and we have marked congruent marks. You guys see that? So if two chords are equidistant from this center point C, then those two chords are congruent. And that would make sense because that circle is going to make it that way. When you come down on that circle, the only way that's going to happen is those two chords have to be in the exact same length. You guys see that? Okay, so that's number 3. Okay, so the next one says congruent chords are equidistant from the center point. So what that is saying is, if I know that the red chord and it's the converse is what it is. You guys see that? If I know that the red chord is congruent to the blue chord, then I can now say that these two distances are the same right here. From C, we can add more letters if we want. F and G. Okay. So if I know that AB is congruent to DE, if I know this, if this is given to me, what do I now know, class? Give me a statement with letters. What do I know? Then GC is congruent to what? FC. Very good. Y'all see that? So it's the converse of number 3. 4. So think about this. 2 is the converse of 1, right? And 4 is the converse of 3. So really, this statement we could write as a biconditional, and this is a biconditional. We could have written these as if and only if statements, right, guys? Because the converse is true and the conditional is true. Okay. Any questions on that? Okay. So another little fun piece of information here. I'm going to go ahead and erase all the stuff. Okay. Do you guys have this? We good? Okay. So let me just go ahead and erase all this. I'm going to just go back to the kind of the plain thing here. Okay. This is kind of where we started. Let me get rid of G real quick. All right. So here's what this next one, our 5th one, is this. A diameter that is perpendicular to a chord bisects the chords and its arcs. That's really important. Now listen to what this is saying. I'll give you a second to write that down, and I'll go back to my picture. A diameter that is perpendicular to a chord bisects the chords and its arcs. Okay? So let's see what that means. A diameter that is perpendicular to a chord bisects the chord and its arcs. So by definition, a diameter is a very special chord that contains the center point. You guys understand that? That's the way you can think of diameters. So if I go to my picture, do you need to write it down more?
Yes, please.
Good job, Sam.
Does Sam get a little dramatic sometimes?
No, he is
No,
not
never,
whatsoever.
never.
It's
Never
always
dramatic.
necessary.
Okay, that was, yeah, all right, just
It's
checking.
always necessary.
There's a little drama there. Yep, a little drama. Okay, all right. So when I go back, when Sam is writing this down, what I'm going to do, I'll explain in my words, what I'm going to do is I'm going to draw a diameter that's perpendicular, let's say, to the blue chord, right? And
All right, I'm good.
so I'm going to take this diameter here, and I'm going to call it, I'm going to just do a green, a pretty green color here. Okay, now I'm going to take a pretty green diameter here. Now remember, diameters are chords that contain the center point. Now, and I'm also going to try to hit that blue one. Forget about the red one for a second. Let's just worry about the blue one. And let's pretend that is perpendicular. Okay, so let's say that there is a right angle here at the intersection of the blue and the green chord. Let's call that intersection F. Y'all understand that? So if I know it does contain the center point, okay, it is a right angle, it is perpendicular. So now what can I say? What's the statement I can say here? What can I say, Tanner? Very good. That theorem is saying that DF is congruent to EF because it's perpendicular and it goes through the center point. Therefore, it bisects the green line bisects the blue one. Now, if this was a right angle here, then it would bisect the red one also. Okay, I haven't said it's right or not. Okay, I imagine it probably is, right? They're equidistant. Yeah, if we take the knowledge before, yeah, it would be also true. So, what do you think the next theorem is going to say?
Convert.
So what would the converse of this statement be?
If diameter bisects chord that's perpendicular.
Okay.
If the coordinates arcs are congruent, then there's a bisector.
Let's see. A diameter that bisects a chord that is not a diameter is perpendicular to the chord.
Wait a minute.
A diameter that's not a diameter.
A diameter that bisects a chord that's not a diameter. So the other chord is not a diameter. It's saying that the blue one is not also a diameter. You guys understand that? Yep. Okay. So it's saying that a diameter that bisects a chord is perpendicular to the chord. Why do we like things perpendicular? Because we get right angles. And why are we so excited about right angles?
Trigonometry.
Because we can use Pythagorean Theorem, most likely, or trigonometry. Okay? So right angles are a very important deal in geometry. Okay? It's very important. Whenever you hear a right angle or perpendicular, that bell should go off in your head that that's important, because then somehow, some way, we probably will some way use the Pythagorean Theorem or trigonometry. There's only 7. Okay. Okay. So another thing, number 7, is a perpendicular bisector of a chord contains the center point. Okay. So what is that saying? I'll let you guys copy it down. Well, I'll just draw a circle right here.
I know what it means.
What does that mean, Chris?
That it's being bisected by a diameter.
Yes. So if I have a terrible circle, you know it's a bad circle when ink to shape doesn't even make it a circle. All right, so let me try that again. Okay, so there's a circle. What number 7 is saying is this. Okay, I think I can just draw it right here. Number 7 is saying this. If we have a circle and we don't know we don't have the center point, all we have is let me do this. We have a chord. Okay, so let me draw a chord really quick. We have a chord, Okay, that looks pretty chord-ish to me. Just ignore this little hangy over part over here. And then we have another chord. We'll make it red, rojo. Okay, and we just take this good old-fashioned chord right here, and we're going to hit that chord, and it's that red chord is going to be a perpendicular bisector of the blue chord. So basically, what it's saying is this chunk is congruent to this chunk, and it is a right angle. So let me give some letters here. So we could say this is A, B, D, E, and F. Okay? So what is Theorem 7 saying? The center point has to be on chord AE. In other words, AE is a what? AE as a diameter. That's why I didn't use the point C. I left the point C because C stands for center for me. So you guys see that?
That's true.
Okay. So this is kind of like a little bit of just kind of some random chord diameter radius stuff that I wanted to go over with you guys. But okay, so let's do some examples. All right, so the first example, do you guys have this? The first example is very easy. Your job, and just copy this down. The hardest part about this problem is copying down the problem. So your job is to copy this down neatly in your notes, and I will give you a second to do that. So this would be like a freebie on a test that I would give you. All you have to do is just know some basic knowledge. Okay?
It's easy. Too easy.
It is almost if you should kind of almost have your intelligence insulted on this problem, okay? Because it's so easy. So all this problem is just saying, do you understand one of the theorems? So can someone raise their hand and tell me what is the value of x and how do you know that? Mr. Martin.
The value of x is 2,
Okay. Why?
and it's because congruent chords are equidistant from the center point.
Now, how do you know that those chords are congruent?
Because of the bisector, it bisects the top.
Do you guys understand
in
that
half.
the one bisects the one in half? Do you guys see that? So therefore, I believe we can say x equals what, class?
2.
X equals 2. Yep. It bisects this one right here. Okay. All right. We're good with that? And we know this is 5 here. So this has got to bisect it down here. So we're good to go. So this is congruent to this. Therefore, x is 2. Any questions? Will, you doing okay with this? Good. Okay. All right. Next problem. Your job, we're going to find the value of x. So this one's a little more funsy in my opinion. Okay? So our job is to find the value of x.
Whoa.
So I want you to think about this problem for a second, and we're trying to figure out how long x is. Now, when I'm saying 16, that is the length of the entire right chord. When I'm saying 20, that is the length of the entire left chord. You guys understand that? Okay, so anyone think they can kind of give us an idea of how we could figure out x right here? So it's a right angle, right? So first of all, let's figure this out right here. So how long is this chunk from here to here? How long is this little green chunk? Why is that 10? It's a diameter, right? So it's a radius. So that's pretty easily said 10, right? Now, how long? We know that's a right angle there, so that's good. So whoever said the Pythagorean theorem is probably on the right track because it's a right angle. So now let's talk about this blue line right here. How long is that? Now it's 8. Now why do we know that that is 8?
The diameter bisects
It's not. This is not a diameter, right? It's perpendicular, right? So if it's perpendicular, then it bisects it. You guys see that? If this distance, right? If this is perpendicular, one of the theorems I believe said this is bisecting it. You guys agree with that?
Sir.
Question?
No, sir.
Okay. So we know, and I guess we could say this is part of a diameter, right? I guess we could say that, right? Bad diameter. But if this is perpendicular, then it bisects it. You guys agree with that? Okay, so now we can use the Pythagorean theorem here. So what would be what's the theorem we would write to solve for x, guys? X squared plus what? 8 squared equals what? 10 squared. So in this case, the green segment is the hypotenuse, right? So we get x squared plus 64 equals a hundo, right? A hundo. And then what are we going to do to both sides? Subtract 64. What is 100 minus? So we get x squared equals 36. Take the square root of both. Whenever we square root both sides, we always do what? Plus or minus, but we throw out the negative because we're in geometry right now, not doing algebra, just regular algebra. So this is going to be x equals 6. Okay, so the key to this is to know that this is part of an imaginary diameter that's perpendicular, therefore it's bisecting. Okay, guys got it? Okay, next problemo. All right, let's see if there's another. Oh, this one's good. Okay, your job. Find the value of x. Okay. Find the value of x. Now, when I say x, I mean the length of the entire chord. Okay, I'm not just saying the part of the triangle there. I'm talking about the entire chord. So be able to explain. I think you guys kind of would know where to go, but be able to explain why you're able to infer that x is what it is. Okay, so I'll let you guys take it for a second here and go from there.
You giving out answers? Huh?
Yeah.
No, Martin, that's only half the link.
It's the length of x.
Okay. Yeah. Wait,
How much
where
did
would
you
it
just
be?
say?
Why is everything make it really not perfect? It's from Clash Royale. Perfect or tall. Yeah.
Okay, so who can raise their hand and tell me how do we start this problem right here? Mr. Chris, how do we start this problem? Okay, so tell me how to start the Pythagorean theorem.
So you do x squared.
X squared Now, is it really x squared?
Half x squared.
So how about we give this a new variable? Let's call this a. Sound good? So we got a squared plus 6 squared equals 12 squared. We all agree with that? So we get a squared plus 36 equals 144. Is that right? Okay, what's next, Chris?
And then we subtract 36.
So a squared equals what, Chris?
108.
C, I agree.
108? So a squared equals 108, right?
And then we take the square root.
Okay, so we know that a equals the square root of 108, right? Okay? Now, what do we know x is equal to?
Okay.
And why do we know it's going to be 2 square roots of 108, guys? How do we know? So here's the question. How do we know that this is also a right here?
Perpendicular.
Because there's really an imaginary diameter here that it's perpendicular, therefore it's bisecting. Okay, guys, get that? Now, I don't know. The square root of 108 can be reduced a little bit. But what is it? Yeah, we can do it in. So this is going to be 2 square roots of 108. If we wanted to put it in simplest radical form, we could, or do a decimal, whatever. Okay. All right, last problem here. Let me see, where is it? Okay, this guy right here is really good. Okay, so what we want to do is we want to find the measure of arc AB. Now, think about this. Okay? Bless you. So, let's remember our information. Congruent arcs have arcs are congruent to their central angle, correct?
Correct.
So if we happen to somehow know that this central angle right here, if we kind of just completed this like this, if we knew this entire angle right here, we would know the measure of arc AB. You guys see that? Now, here's the deal though. I believe this is an angle bisector just by looking at it, right? I think we can have enough geometry to assume that that's an angle bisector. Okay, see that? So if we figured out this theta right here and multiplied it by 2, that would be the central angle, and that would be the measure of this arc right here also. So Sam has said we don't have enough information to use the Pythagorean theorem, do we?
Yeah, we do.
Yeah.
Oh, we good.
You
15.
can find out 15.
No, we don't.
Yes.
No.
Oh, yeah.
But we need to know the angle, right?
Right.
So what do we have? So we have a theta, and then from theta we have an opposite and a hypotenuse.
Opposite over adjacent.
So what is that?
Oh, opposite over hypotenuse.
What is the opposite and the hypotenuse?
Sine.
So we know that sine of theta is going to equal 15 over 17. So we are going to need trigonometry because we need the angle. But how are we going to, and we're going to do it in degrees, how are we going to figure out what theta is?
Take the inverse sine.
So we're going to take the inverse sine of both sides. So when we take the inverse sine of 15 over 17, what is the inverse sine of 15 over 17?
1.1.
Is it in degrees?
In degrees, yep. What is it?
44.9.
We get about 44.9, or we'll round that to 45 degrees. And so what is this angle right here, guys? What is this? That's a 90-degree angle.
That's crazy.
So this is 90. All right. So ladies and gentlemen, that concludes our lesson on chords, diameters, perpendicular, all that good stuff. And plus a little vertex. So we got a lot of good knowledge in here today, right? Okay. So
When I put it in the calculator, it says 62.9 degrees.
did you do the inverse sine? What did you do the inverse sine of?
Arc sine of 15 divided by 7.
Not gonna lie, when I get a school
We do.
my favorite school is
Inverse sine
wow,
of 15 divided by 17.
Yeah, and then all of my
So I almost, guys, let's go back to this really quick. I don't know if I agree with the 45. Do we? Hold on. Let me just make sure on my math. So we want to do, let's see here. So it's opposite over hypotenuse, correct? So I'm looking at and what am I doing wrong? I'm doing sine of inverse sine. Let me make sure I'm in degrees. I am in degrees. And Martin and I are both coming up with the answer of 61 degrees. Try that again. Inverse sine of 15 over 17. Try that again. So it is not 45 degrees. This is actually going to be about 62 degrees. Thank you, Martin. And then we're going to multiply that by 2. So, and this it makes a lot more sense. This is about 124. It felt wrong. It just felt wrong to be a right angle. It didn't look like a right angle. It felt just not right. Something was wrong with my math soul there.
Also, the things touching the right angle would have to be close to each other.
A lot of good stuff there, right? Okay, guys. Do you guys need homework on this, or you think you'll be good? We'll practice more tomorrow. Sound good? All right, let's call it good. I'm now going to stop.